Thank you very much, Mark. And thank you for inviting me. It's a real pleasure to be here and be invited to speak. So the title of my talk is Byte, Character, Subword, Morpheme, Word, Phrase, which representational unit is best for deep learning? And I actually had to compress the talk a little bit since it's a shorter format, but hopefully it still makes sense. Otherwise, you can ask questions at the end if I omitted something that shouldn't have been omitted. So the question I want to start with in this talk is, where is meaning? If you have a deep learning architecture, where is the meaning of natural language represented in that deep learning architecture? So that's more of a theoretical approach. So those of you who are more practically minded, then the following part is very practical. It's BERT, where I'm going to try and apply the insights from the theoretical part to BERT. And BERT is one of the new generation of contextualized embeddings, which is really an amazing recent advance in natural language processing. And the last slide is then an outlook. So where's meaning in deep learning? I first want to review the basic embedding concepts of words, characters, and subwords. And in each case, I'm going to ask, where is meaning represented? And one thing that's, Mark already alluded to that, one thing that's very important in this context is the role of ambiguity. So in each case, I'm going to talk about the role of ambiguity. Okay, so let's review the basic word embedding concept. And I'm sure everybody here, or most people, are familiar with that, but let's just make sure that we're all on the same page. Okay, so this is a picture I'm going to use a lot. So at the lowest layer here, we have one hot vectors. My example here is red suit for sale. So this is the one hot vector for red, the one hot vector for suit, for sale, and for in sale as well. Then we have here an embedding matrix. The embedding matrix has as many columns as the dimensionality of the space, and the number of rows is the vocabulary size, and each row is then one embedding. Then the next row is the next layer is the embedding layer. You get that by multiplying the embedding matrix with the one hot vectors. And then we have one or two or more hidden layers. And so the hidden layers I'm showing like this here. So this is the representation you get at hidden layer 1, and it's a function of the embeddings. So these 4 embeddings here, and also there are some parameters A. And I'm just going to depict the parameters A like this, like a matrix. But what I want to say here is I want to abstract away from any particular architecture. So this could be a fully connected layer. It could be a CNN. It could be an RNN, an LSTM. It could be a transformer. So it's just an abstract representation for a layer. And then the same here for the next layer, H2. We have a representation here at layer 2. OK? So that's the basic idea of word embeddings. And so the question now is, where is the meaning represented in this architecture? And the meaning is in the embedding. I'm not going to talk about that in too much detail. I think we're all familiar with embeddings, but the embedding vectors represent the meanings of the words. So for example, the meaning of red is represented in the embedding of red. So this is here in this embedding of red. Now, it's a little bit more complicated for an ambiguous word. For the word suit, for example, it has 2 meanings, the lawsuit meaning and the garment meaning. It has more meanings. Let's just focus on those 2. The lawsuit where you sue somebody and the suit that you wear. And those are also represented in the embedding. Now, some people have a problem with the idea that you have a single vector and it represents 2 different meanings. But there's actually no problem with that, because if you have a 100-dimensional, 300-dimensional vector, then that's a lot of capacity to represent things. And so there's no problem in principle with representing 2 different meanings in one vector. Okay, so the meanings are represented in the embeddings. And then in the case of ambiguity, like for the word suit, you have then to select one meaning, the contextually appropriate meaning in that context. And that is, in this case, garment. In the context red suit for sale, the selected meaning is garment, and that happens in the first layer. It could also happen in layers that are further up if it's a more complicated disambiguation process, but in the simplest case, the representation at layer 1 will have selected one of the meanings. So in the case of ambiguity, hidden layers select one of the meanings based on context. Okay, so that's word embeddings. Let's look at the same diagram for character embeddings. So for character embeddings, it's basically, again, the same. We have the one hot vectors here, we have the embedding matrix here, we have the embeddings here, and then we have further hidden layers. The only difference is that now we are on the level of characters. So this is the one hot vector of S, and this is the embedding of S. So where's the meaning here for character embeddings? The meaning is in the weights of the hidden layers, not in the embeddings. And just a terminological note, I'm going to call, when I say weights, I mean the weights of these hidden layers, and I'm going to distinguish that from embeddings. Of course, embeddings are also weights, but it's just easier to talk about it if I make this somewhat arbitrary terminological distinction. So when I talk about weights, I mean A and B. When I talk about embeddings, I mean E, okay? So the meaning is in the weights. Why is that? So in particular, the meaning of the lawsuit meaning and the garment meaning of suit, that meaning is here represented in the weights of the network. Now, why is that? Couldn't it also be represented in the embeddings? That's not possible because if you think about the character S in English, it is part of thousands, tens of thousands of different words. It's just not possible that a single vector, the vector for the letter S, represents all of these words, the meanings of all of these words. So the meaning is not in the embedding layer. The meaning is constructed as we go up the hidden layers. And if it's a simpler meaning, it's constructed in the first hidden layer. It may also be constructed in layers further up the stack. And so what we get here is that both meanings of suit, the lawsuit meaning and the garment meaning, are represented at this first hidden layer. And then in the case of ambiguity, we again have to select one of the meanings based on context. Let's assume we have the same context here, red suit for sale, and then we get the disambiguation. It just happens later here in the layers than before. Okay? Is that more or less clear, or is there somebody an issue with this? Okay. Then to summarize, where's the meaning in deep learning? For word embeddings, the meaning is in the embeddings. For character embeddings, the meaning is in the weights. Now, why is that? Why do we get this difference? And the reason is that the meaning of a sentence is a compositional function of the meanings of its words. But the meaning of a word generally is not a compositional function of its characters, and that's the arbitrariness of the sign. And so I assume that many of you here don't have a strong linguistics background, so let me just talk briefly about these concepts. What I'm referring to is the principle of compositionality. The meaning of a complex expression is determined by the meanings of its constituent expressions and the rules used to combine them. The meaning of a complex expression is determined by the meanings of its constituent expressions and the rules used to combine them. And by rules here, they correspond in deep learning to regular processes, that is, non-idiosyncratic regularities in how meanings are combined. Of course, we don't have rules in deep learning, but we have something equivalent, the regular processes that everybody knows about English when they learn English. So let's just look at a couple of examples for those of you who are not familiar with these expressions. So here we have the compositionality from words to sentences. So we have 3 sentences here. John eats apples, Mary builds houses, Kim writes books. And on the right side here, I've shown the meaning in a kind of logic type representation. And you can see that this is a very regular process. That's part of what you learn when you learn English, that if words are put together this way, then you get this type of meaning. So the first word here is always the first argument of the predicate, the second word is the predicate, and the third word is the second argument of the predicate. So that is a typical example of compositionality. And the same for this example, the car is red, the city is big, the orange is yummy. Again, we have a very regular process of composing the meanings of the words to the meaning of the sentence. So that's compositionality. And now non-compositionality, which is what you get when you go from characters to words, if you combine the meaning of S, U, I, and T to the meaning of suit, that's a completely idiosyncratic process that you cannot use for any other word. You can use it for other morphological variants, of course, of suit, but not for a different word. And the same for house and the same for car. If you combine C and I, A and R to the meaning of car, that's completely idiosyncratic and non-compositional. So to come back to our question, why this difference? For word embeddings, the meaning is in the embeddings. For character embeddings, the meaning is in the weights. The reason is this difference between compositionality when we go from words to sentences and non-compositionality when we go from characters to words. Of course, word sequences can be non-compositional too. So this slide basically is just saying that I simplified things a little bit and that it's in reality more complicated. So of course, word sequences can be non-compositional and character sequences can be compositional. So especially in the case of morphology, you have partially compositional character sequences. If you look at the word database, of course, it has something to do with the meaning of its parts. And hot dog would be an example of a non-compositional word sequence. Hot dog is not compositional. It's a Frankfurter in a bun, and a Frankfurter in a bun has nothing to do with a dog. So it's non-compositional. So to be a little bit more precise, the meaning for word embeddings, the meaning is mostly in the embeddings for compositional word sequences, but partly in the weights for non-compositional word sequences. But it's still the case that for character sequences, the meaning is in the weights. Now, what about subwords, BPEs? And so this is one of the interesting developments, recent developments in deep learning, that very often people use subwords to represent natural language. That is something that wasn't really very common before. And so what do I mean by that? And I'm not going to, for those of you who really are very deep in this, I'm not going to make a distinction between subwords, BPEs, word pieces. I'm just going to say subwords and mean all of those. So here's an example of subwords as they are used in BERT, this architecture that's going to be the second part of the talk. So basically what we're doing is, for most words, we just represent them as word units as we would do in regular natural language processing. So upon is represented as upon, which as which, the as the, and so on. But then for rare words like dispatched, O'Banion, hijacking, we break them into parts and represent them as parts. So the hash here means join the subword to the previous subword, so that you get dispatched. So it means I'm not starting a new word here, I'm continuing the previous word. That's what these two hashes mean. Now, why do we do that in deep learning? We do that because for many scenarios, we need a relatively small vocabulary, especially for language modeling. In language modeling, we predict a word in context or the next word, and so we have a softmax over all possible alternatives, all units that we have in the vocabulary. And if that softmax gets too big, then it becomes inefficient and difficult to learn. So what we'd rather do is somehow limit the vocabulary to, let's say, a good number is tens of thousands, let's say 20,000. And that's what you achieve by the subword representation, because each of these subwords is frequent enough that it's in the top 20,000, but the word dispatched and the word O'Banion and the word hijacking, they are not frequent enough and wouldn't be in the top 20,000. So it's a trick, and it's pretty I would say, lame heuristic how these subwords are generated, but it seems to work pretty well. It's a trick to make sure that our vocabulary size is small. So how does our picture, what does it look like for subwords? So I want to ask, where's the meaning for subword units like hijack and ing? And I'm actually going to use the example dashing. So dashing in subwords, as Bird uses them, is represented as two subwords, dash plus ing. Dashing has the meaning handsome, as in cut a dashing figure. But it actually also has a compositional meaning. So dash can mean run, and ing is the progressive in English. And so if you put the two together, you get running in the progressive, and then it has a meaning, for example, in I'm dashing off. And I'm going to write that as MR plus MPs, and it's a completely compositional process. So what does our picture look like for for this case? It's again the same, except now we have subwords here and subword embeddings here, and then we have our hidden layers again. So where's the meaning here? So MH is handsome, MR is run, MP is progressive. The meanings run and progressive are in the embeddings because they are units, and we're going to learn the regular meaning of these elements in normal embedding learning. So they are here. This here is the meaning run of dash, and this is the meaning progressive of ing. And then that's a regular process, so we can compose those two meanings in a regular way, and then we get the meaning dashing, running, which is here denoted as MR plus MP. Now what about the handsome meaning of dashing? Well, that's an idiosyncratic composition. When you put together dash and ing to get the meaning handsome, you cannot apply that idiosyncratic composition function to any other word in the language. So that is, again, represented in the weights. MH, like for a character level model. And so then you get at the first hidden layer the representation of both possible meanings, and then you again need a disambiguation process to get the meaning that is invoked in context at the higher layers. So you can see that subwords are somewhere in between characters and words. They have properties of words, and that the embeddings actually represent meaning, but that they also need lots of idiosyncratic composition functions, more than words do, to actually put the meaning together for things like dashing handsome. So to summarize this part of the talk, where is the meaning? For words, the meaning is in the embeddings. So it's here with a few exceptions like hot dog. For characters, the meaning is in A, or maybe also in B, but mainly in A. So there's no meaning in E, all the meaning is in A. And subwords are somewhere in between. The meaning is mostly in the embeddings, but a lot is also in A. Okay, so why do we care about this? So the meaning can either be in the embeddings or the weights, and there's different trade-offs you can make. Why is this a question we want to discuss? So my hypothesis here is that meaning in the embeddings is easier to learn. And why is that the case? The first reason is that you have no potentially catastrophic interference. If dashing has its own embedding, then that means D parameters reserved just for the meaning of dashing. So let's say you have an embedding for dashing, 300 dimensions. Those 300 parameters are reserved for dashing. No other word messes with that. It's just there for dashing, for learning the meaning of dashing. Okay? In contrast, if you try to compose the meaning of dashing out of two subwords, dash and ing, then the same weights, these composition weights, are used for dashing and for all other compositions. So let's look at the picture. So I'm talking about this matrix A here. This matrix A, and potentially also the higher layers, it does all the compositions for us. And in particular, the idiosyncratic compositions like dash, ing, and so on. And there's no modularization here that few parameters are for one composition and some other parameters are for another composition. It's all mushed together. Any parameter in A is going to have an influence on the composition of dashing and on all other idiosyncratic compositions. So that's not a very nice machine learning setup that we have this mess where everything is thrown together, all of these different idiosyncratic compositions. So that's the first problem with, the first reason why meaning in the embeddings is easier to learn. And the second is meaning in the embeddings is that embedding parameters are cheaper than weight parameters in terms of learning. And so if you look at Google News embeddings, that's about 10 to the 9th parameters. And that's something that's pretty easy to learn. I mean, nowadays, I think any university lab, any company can basically reproduce this experiment. It was more difficult, I guess, when was it, 6 or 7 years ago, but now that's not that difficult to do. That's kind of standard, state of the art now, even for such a large set. But for character level models are still very difficult to train. So at EMNLP last year, a very impressive Google character level NMT system was presented, and that has an order of magnitude fewer parameters. And why is that? Because it's so difficult to train it. It's so difficult to train that like maybe the best group in machine translation at Google had to work very hard to make it work. And this is not right now standard machine translation because it's so difficult to train. And in the GPT-2 paper, for those of you who are familiar with that, they also said, we would have loved to do this. Well, they didn't say it that way, but I think they really wanted to do a character level model, but it was just too difficult to train. And so they abandoned that effort and went to subwords. So it's much more difficult to train, to learn character level parameters than it is to learn embedding parameters. Okay, so those are the two reasons that I think we should give preference, if possible, to learning parameters, to embeddings, rather than trying to do everything in the weights of the regular network. Okay, so that was kind of my theoretical motivation for the second part of the talk. So now we're going to be more practical and look at a particular task here. And so this is going to be about BERT. How am I doing on time?
There's time until 10:15, including questions.
Including questions, okay. Well, I should cut some stuff from the talk that I shouldn't have cut, I guess, since we started earlier, but that's okay. We'll just have plenty of time for questions then. Okay, so this is about, this second part is about contextualized embeddings. And maybe I'll just do that since Mark asked me that I also have to be on this side of the lecture hall. So this is the BERT, and it's a transformer architecture. So each layer here is a transformer layer, and I'm not going to explain that in detail. It's a language modeling setup, and it uses word pieces as input. So this is here the input layer, and these are word pieces, subwords. And it's a language modeling setup. So what we're trying to do is, let's say we have here, let's say this is dash of dashing, and we want to predict dash here, the subword dash. And what we do to do that, to train the model, is we're going to mask dash here. So we're giving the full context of the sentence to the model, except we mask this one word, dash, and then the task of the network is to predict that dash occurred here. So this is a task that's difficult, but humans can usually learn it, solve it pretty well. And so if you train a neural network to mimic this task, then there's some hope that it has learned something interesting. Okay, so that's the basic task of the model. And the main innovation here is that it's a combination of a transformer, which is completely bidirectional. So there have been similar models before, but they were not completely bidirectional at all levels, and giving each unit here access to everything on both sides of the input, both sides of what you need to predict, and this novel training setup. I mentioned the masking, and there are some other elements that also seem to be important, like context sentences. So yeah, so that's BERT. It's actually not really a huge breakthrough that made it possible. I think it's just that they put together many different elements in a very nice and intelligent way, and that's why it's really such a great model. And so, yeah, and why is it, has it been received so well? Because it performs very well. Large performance gains on many tasks. So this is just one example where it seems to be a lot better by a pretty impressive delta than previous work. So the question I want to ask is, has BERT learned the meaning of language here? Good performance does not imply that it has, because a lot of deep learning makes correct predictions based on correlations, not based on true understanding. So it doesn't really answer the question here. So how can we determine whether BERT has a true understanding of meaning? And so this part of the talk is based on work by Timo Schick. He's one of my PhD students. Rare words, a major problem for contextualized embeddings, and how to fix it by attentive mimicking. And you can download that from arXiv. And so Timo's idea was to introduce probing tasks. That's something that's done a lot right now, to probe neural networks so that we understand better what they do. And so he came up with a particular type of probing task that is really nice for BERT, a nice match for BERT. So let me just jump into the first one, antonyms. So we define patterns like this. W is the opposite of blank, period. And the W is replaced by a word, and we have a set of words. So we have an evaluation benchmark, which comes with lots of information. One part of the information is with which words W can be replaced. So new is one possibility here. And so we get this instantiation of the pattern. New is the opposite of blank, period. Then we have a gold standard, which is derived from WordNet. And the gold standard tells us the true answer here is, or the true substitution here is old, because new is the opposite of old. Now, BERT predicts a probability distribution W given context for this blank. So now we can ask BERT, what do you think should be put there in the blank? And it will give us this probability distribution, and that gives us a very detailed view of what BERT is internally thinking, so to speak. And if the prediction of BERT for that blank here is correct, then it gets a point. And by correct, I mean that the word that gets the highest probability in that probability distribution, if that's the correct word, then BERT gets a point. And I'm going to write that like this. New is the opposite of blank, period. And so what BERT should do to get a point is to substitute old here. OK? And just to be sure that we're all on the same page, so we're going to put this pattern in here. New is the opposite of blank. Let's say this is the blank. And then, so we put the mask token, BERT's mask token here. And then BERT has to predict up there the correct token. So it's going to output a probability distribution. And if the most probable word here is old, then BERT gets a point. And this probing task is inspired by the GPT-2 paper, which is a very nice paper where they show that if you just train a language model, you actually don't have to adapt it to any particular task if you find the right wording in natural language to suggest that task. So for example, they have an English sentence, and then they just append to that English sentence the French translation of this English sentence is colon, and then the language model sometimes, at least, produces an English sentence, the English translation. So it's a very nice idea, and it's basically our patterns are modeled on this idea. And so we always use several patterns. Let me introduce the other patterns for antonyms here. W is not blank period. Someone who is W is not blank period. Something that is W is not blank period. And W in quotes is the opposite of blank in quotes period. The reason we use several of these patterns is we are not interested in the question, has Bird understood the patterns? Our question here is, has Bird understood the word? And the word in this case is new. That's what we want to know. So we actually run Bird on all of these patterns, and then we choose the best result. Because the patterns are not really so important. What we really want to know is, has Bird understood the word new? So we always choose the best result over all of these patterns. And of course, if for one of these patterns, Bird does find the correct word, then it must have understood the meaning of new, at least this aspect of the meaning of new. So that's kind of our basic assumption in setting it up this way. Okay, let me go through the other three probing tasks. The second one is hyponyms. The first pattern here is W is a blank period. AW is a blank period. W in quotes refers to a blank period. W is a kind of blank period, and a W is a kind of blank period. And an example here would be basketball is a blank period, and then Bird has to fill in actually a hypernym. So hyponym here in the naming of the probing task refers to basketball. So Bird here has to fill in a hypernym of basketball, and the same for this pattern. Okay? Third one, co-hyponyms. Here the first pattern is W and blank period, and W in quotes and blank in quotes period. An example here would be harmonium and blank period, and here Bird has to put in a musical instrument. So or immorality and blank period, here it has to put in some immoral action. Okay, and the last one is correction. That's a little bit different because it's not derived from WordNet. We just created spelling errors by applying some operations like transposition and deletion and insertion of characters. Here the two patterns are, the first one is W in quotes is a misspelling of blank in quotes, period. And the second one is W in quotes, did you mean blank in quotes question mark? So the examples here are simulation is a misspelling of blank in quotes, period, and so Bird has to substitute here simulation. And pinnacle, did you mean blank in quotes question mark? And Bird has to put in pinnacle with 2N. Okay? Okay, so if we run so now the nice thing about the setup is that we can very easily generate a large benchmark of such probing tasks in these 4 different categories. That's basically something you can do programmatically by just using WordNet and mining it for appropriate word pairs. And I should say that for co-hyponyms and hyponyms, of course, there are many possible answers. Even for antonyms, in some cases, there are several answers. There are many musical instruments, so it's not just one word that's correct. There are many words that are correct. But of course, the number of words that are incorrect is much, much larger by a large factor. So we can easily generate a large benchmark here, and we can run Bird on it, and then we can see how well did Bird do on these probing tasks, and we infer from that how well has Bird learned the meaning of these words. The evaluation measure we use is mean reciprocal rank. So what we do is we actually don't insist on the correct answer at the top, as I suggested earlier, but what we do is we take Bird's ranking at a particular blank, what Bird wants to substitute, and then we go down the list to the first correct answer. And that has a rank. We take the reciprocal of that, and we take the average over all those reciprocal ranks. So that's the MRR measure. mean, reciprocal, rank, and that's what we use for evaluation. I'm not going to talk about position at 3 here. And so what you can see is that for frequent words, so we had the pattern new is the opposite of blank period. New is a frequent word. For those frequent words, BERT does pretty well. So this measure here, MRR, ranges between 0 and 1. And these are numbers that are pretty good for in natural language processing. I mean, if you see these numbers for an MRR evaluation, you're usually happy. But if you look at rare words, the numbers are much worse. So we get, this is the highest here, 0.284, but all others are below 0.25. So what we can conclude from this is that for frequent words, the meaning of frequent words is learned well by BERT, but the meaning of rare words is learned poorly by BERT. And why is that? So there are two different reasons for that. So one is that BERT's subwords are a poor representation of the rare word. So here we have one example, ophthalmoscopy, which I guess means the treatment of, or investigation of the eye with medical instruments. And you can see that this is a horrible representation of ophthalmoscopy. It's torn apart into 6 subwords, and these subwords clearly are not meaningful units. So to put together from these 6 subwords the meaning of the word is as hard as it would be in a character level model. So this is a bad representation. And the second reason that BERT doesn't do well for rare words is that the decomposition, the segmentation might be okay, but BERT has not learned the composition function. So that's the composition function at the higher layers, for some reason, has not been learned. An example for that is here that we found in our experiments is resign theon. That's a misspelling of resignation. And you can see that the segmentation is actually good because resign is the meaning carrying unit, so that's okay. But BERT was not able to combine these 3 units to the meaning of resignation, or to a meaning that had something to do with resignation, so it failed there for lack of a composition function. Okay, so the meaning of frequent words learned well by BERT, meaning of rare words learned poorly by BERT. Well, how can we solve this problem? How can we do better than BERT is doing today? And so we are combining 3 different ideas. The first idea is change as little as possible. The only change we'll make is to replace BERT's embeddings of the rare word with a new improved embedding. Everything else stays the same. So for example, we take ophthalmoscopy, these ugly 6 subwords, we throw them out and we replace it with a single embedding for ophthalmoscopy. And so in particular, the composition weights in the higher layers are not changed. So, I mean, just to look at the picture again. So we leave everything the same, by the way, including the lines that go from here to here. So the connection between the embedding layer and the first layer of the transformer. The only thing we change is this embedding layers. We throw away some of the embeddings and substitute new embeddings. And part of the motivation is that this is really a great advance, so why mess with it? We're just going to leave it the way it is, except we are going to improve the embeddings. So that's the first idea. The second idea is use both surface form and contexts of the rare word to learn a new embedding. If you think about how BERT is trained, it is trained to predict a word from context. But it's not looking inside the word, the character string of the word. That's not part of the model. And that's an obvious thing you want to do in many cases, at least as an additional source of information. So, and ophthalmoscopy is actually a great example, again, because it has the root ophthalmo, which is eye, and scope, which is instrument. And so if you have learned those 2 meanings, then you can put together the meaning of ophthalmoscopy. And the third idea is mimicking. Learn a new, improved representation of a rare word by training a model to predict existing representations of frequent words. Actually, unfortunately, I don't have a good slide on that, so let me explain that without the slides. So the idea is actually very simple, and it's not our idea. It's from Jacob Eisenstein's lab at Georgia Tech. And you can also do it for word embeddings. So let me explain it for word embeddings. So you have a corpus, training corpus, you run your embedding algorithm on it, and it produces word embeddings. Now you go to a test set, and you want to do some task there like sentiment analysis. But unfortunately, in that test set, or when you apply it to data in a real application, there are going to be words that didn't occur in the training set. So what OV words? What do you do about these words? And so what mimicking does is you go back to the training set, so you have your embeddings, and now you train a second model, and the second model takes some information about the word, and the information we use is the surface string of the word, simply the character string, plus contexts of the words, just the sentences in which it occurred. And from that information, we try to predict the embedding in the training set. And now we have a second model that can reproduce the embeddings that we had learned before. And the second model we can actually transfer to the test set. So now we have a new word that didn't occur in the training set. We can collect the information about that new word, its character string, the contexts we have seen it in the new data, and we can produce an embedding. And that embedding is compatible with the embedding space that we created before. So we can directly use it in our model. It's going to work not quite as well, but almost as well as the embeddings we learned before in the training set. So that's the idea of mimicking. And we're basically applying that here to BERT. And this is the particular architecture we're using. So what you see here is first the split in form embeddings and context embeddings. So this is where we look at the character string, that's the left part of the model. And S1, Sn, and so on, those are simply character n-grams. So we learn a representation for each character n-gram. And then we just take the average here. And the context embedding, so each C1, Cm is simply a sentence. And the representation of that sentence is the sum of the embeddings of the words in that sentence. So then we have a representation for each sentence in which the word occurs. Then we have the self-attention layer. The purpose of that is to focus on important contexts. Because if you think about what kind of context a word can have, some of them are not going to be informative. For example, if you have the context, X is great, that doesn't really tell you that much about the meaning of X. But other contexts, like X is a musical instrument, are very telling about what a word means. So the self-attention layer, which I can explain in more detail if you ask me about it, puts more focus on the informative contexts and tries to get rid of the uninformative context. Again, we take an average here, and then we have a gate, because in some cases, the character information is more informative, and in other cases, the context information is more informative. And this is a trained parameter that gates how we mix these two sources of information. So that's our mimicking model. This is the second model that I talked about, which is trained on the old embedding space, but now we can apply it to any word we want to. And here in this case, we apply it actually to rare words that may have embeddings or that do have embeddings in BERT, but they have bad embeddings in BERT. So we are not using mimicking to create embeddings for new words, but to improve embeddings for rare words. Okay, and if we do that, then we get a lot better performance for rare words. Not so much for hypernyms, although we get a good improvement there too, but definitely for antonyms and for co-hypernyms and for corrections. The numbers are much, much better if we do this mimicking. So what we've done here is we've just thrown away the old embeddings, done mimicking, and replaced the old embeddings with the mimicked new embeddings. Doesn't work so well for frequent words, so this, we have a slight improvement here, I guess, but it gets worse here. So that shows you that BERT is actually doing a pretty good job at learning embeddings for frequent words. And our method doesn't improve it or makes it even worse if we apply it here. So what is the reason that this works? So one big reason is that BERT plus AM uses word representations, not subword representations. And as I said in the first part of the talk, the composition function, the network weights, are no longer needed. And it's much more difficult to learn an idiosyncratic composition function in the weights of the parameter. Oh, 2 minutes left. I thought I had so much time. Then
You can also have 5.
okay, well, let me just finish then.
Yeah.
Right, so this picture I think shows it well. This is what BERT does. This was our dashing example. It operates with subwords. And so we've moved BERT much more in this direction where it uses word embeddings instead of subword embeddings. And that's I think, the main takeaway here. The second reason is that attentive mimicking taps information for representation learning that BERT does not have access to, in particular, character strings, the surface form. We also use attention. That also has an effect, although not as big as we would hope. And also we have the difference between bag-of-word model and a sequence model. BERT is a sequence model that's in theory much more powerful than a bag-of-word model, but in a sparse data situation, you may want to use a simple model because the parameters are easier to estimate. Okay, so then the outlook. Intuitively, each unit seems most appropriate for some cases. Hot dog, I think, ideally you want to represent as a phrase, because that's not, as I said, there's nothing to do with the dog. Bloom, you want to represent as a word, I think. So there are many cases where you just want a word representation. Blooming, you want to represent as subwords because it's a completely compositional. I guess there's actually also non-compositional. I should have found a better example, but there are examples. Let's say bring plus ing, that's completely compositional. So we should use a representation that takes account of that compositionality. So in that case, we should use subwords. Simulation, in that case, for spelling correction and cases like that, we need to, and also things like Brexit or portmanteaus and things like that, we need access to the character string. What I've presented here, BERT plus AM, is a partial fix, but it's only a partial fix. So the question is, can we start with an inventory of all units and select the appropriate one for each case? So can we be more diverse in the units we use and always use the right unit for each case? And I've given you some examples on the slide for when to use which unit. We could use the lattice of all segmentations as embedding layer, but that would be a clean and nice solution, but I think that's too big and too noisy, and I don't see how you can train that end-to-end in a deep learning architecture. But if somebody has ideas on that, then I would be very interested. So that's future work to come up with such a formalism that can do this, can use a mix of different representational units. And that's the end of my talk.
Thank you very much also for making up with the time. I think you spent the time very well. Other questions?
So if I wanted to use BERT for grammar, what is the best way to proceed? And how many people have tried it so far?
Oh, I thought there were German models available. Does anybody know? Yeah, there are German models available, so you can just download them and run it.
Thank you very much for the presentation. I have two questions. The first question is, when you were comparing BERT to the rare words and frequent words for the problem tasks, why the correction of typos has no metric for the frequent words?
Because except for very, very few exceptions, there are no frequent misspellings. Misspellings usually are, I mean, fuchsia, for example, the misspelling of fuchsia, I think, is more frequent than the correct spelling. But in most cases, the misspellings are not frequent. At least for the type of text that BERT is trained on. Of course, if you go to social media, then maybe you have also frequent misspellings.
So do you think that the correction factors to the frequent words could be somehow assisted by BERT?
Could somehow be
Assisted by BERT if we have a program task of frequent words coming.
No, I'm sorry, this may be a misunderstanding. The question is not, is the correct form of the misspelled word frequent? The question is the misspelling itself frequent? So that's the criterion here. So is the simulation, for example, is probably also a frequent word. But in our statistics, it's counted as simulation, counts as infrequent, because that misspelling is infrequent.
Okay, I see. And something else, when you explain the three ideas how we can fix the problem, can you please elaborate a little bit on the second idea, before the mimicking?
I mean, that's just referring to the fact that we have these two different that we want to use these two different sources of information. So maybe you're familiar with fast text. Fast text also uses the form part and the context part. So because both what's inside the word, the character string, gives you some information in some cases about the meaning, but the contexts too. Word2vec only uses the context. Word only uses the context, but it's clearly advantageous to use both.
So this line corresponds to the second idea, not the third idea of mimicking. So what is the difference between idea 2 and idea 3?
I mean, mimicking is just a very general concept that you can use any information you have a word to predict its embedding. You could, for example, also, if you are in a social setting and you know these 43 people have used the word, you could try to predict its embedding just from those 43 people. So any information can be used in mimicking.
Okay, thank you.
Why do you have your slots in the program task always at the end of a sequence? Since BERT's advantage compared, for example, with GPT is to predict the slot filling in the middle of sequences.
Good question, good question. Can you suggest a pattern for the 4 tasks we have where it would be advantageous to have the blank in the beginning?
Yeah, for example, the opposite of ... is new.
Right, but that I think is a more difficult pattern. We could just invert it, of course. We could say instead of having the pattern W is the opposite of blank, we could have the pattern blank is the opposite of W. That's interesting. We should try that, yeah. I mean, we should do some analysis to see how good our coverage is based on the patterns.
May I ask just a follow-up question? What is the chances that your pattern already occurred in the training data? Because, I mean, something like, oh, this is the opposite of you might have been there, so it's not a question of understanding, but just repeating.
Yeah, that's possible, yeah. I mean, I don't think it's a huge problem because, let's say for new occurs in so many different contexts. BERT is not set up to memorize a particular context. So I think a sentence like new is the opposite of old is just going to, the particular content of that is not going to be important. It really has to try to generalize away from that.
I was just wondering if you could comment on the direction that you're taking in comparison with the parallels of how humans learn themselves. So as an example, a child usually learns character level first and then moves on to phonemes, and then by the time you're an advanced reader of a language, you may have seen the famous images going around on social media, if you can read this, your brain is smart, but all the characters are swapped, right? So we go to a kind of word shape with context. You could also imagine if you're learning a new language and a new script, such as Greek, that again you start character level, you move quickly to phonemes, and so on. How does that parallel with the directions you're taking here? Does it?
I'm very interested in looking at cognitive neuroscience and psychology, child psychology, and getting insights from there. But I don't think in this work there is any such insight. I don't think. I mean, of course, people can learn words from context, but usually the most common case of that is that people learn context either in an educational setting, somebody teaches them what the word means, or there's a definition, or it's something that you learn from a few contexts, 1, 2, or 3, where you kind of intuitively get the meaning of the word. If it's an interactive setting where someone points at it, then a single use is sufficient to learn the meaning of the word. So it's. I don't think it has much to do with what people do, and I would disagree with the point of view that you first learn the character level and then you learn the word level, because we're talking about meaning here. And I think meaning is learned from for entire units by children first. And then maybe later they realize, oh, there's morphology, and I can systematically change the meaning of a stem and things like that.
So meaning and text are actually learned independently. So the textual representation of a word is learned independently from the meaning of the word.
I mean, the model actually tries to get around that, right? So that's why we have these two parts. The textual representation is the form embeddings, and the text is the context embeddings.
Thank you very much for the talk. Small detail, how do you determine which is a seldom word and which is a common word? Is it based on a reference corpus, or is it based on the tokenization scheme?
Or is it based on?
Like the tokenization that is done by BERT, if it's tokenized as an entire word, or if it's put into 6 different subword segments?
No, we use a corpus. I think Timo used the Wikipedia corpus, one of the standard Wikipedia corpora. And of course, that's a limitation, because what we really would want to know is, was it frequent in the corpus that BERT was trained on? And we don't know that. So we are not trying to make inference from the BPEs saying, okay, this must have been a frequent word. We just count it in Wikipedia.
Thank you.
Thank you for this talk. I was wondering, when you were looking at the misspelled words, were you looking at actual misspellings? So, because there are sometimes misspells that are just misspelled in context, so they are actual words, but in that specific context where they occur, they're just wrong?
I think maybe there's 2 parts to the question. So the first one is, these are not natural misspellings. So that's another potential limitation that we didn't. I don't think BERT would be able to handle the subset of natural misspellings better than the ones we have here, but that's certainly a limitation of the study. So you're talking about, is an example of what you're talking about, that you have form and you mean from?
For example?
Yeah.
Come up with an example. That's the example.
Yeah, and that, so we only, I actually don't know whether, I assume Timo checked this. So it's very unlikely that you get a correct word if you apply one of these spelling, if you apply spelling noise. But I hope he checked that you didn't get a real word, but I'm not sure.
So we have time for one more question. I also have a follow-up question with regard to the probing. And you had one task where BERT was expected to find a co-hyphenon, right? And you had W and blank. And I thought that was a bit unfair, because it can also give you collocations like counting prejudice, war and peace, crime and punishment.
But aren't all of these things the same in terms of cohyponyms?
Pigs and troughs.
I think most of them are cohyponyms, and notice that I use cohyponym plus. So it's not a true cohyponym, but we relax that by looking at, I'm not sure how Timo exactly defines it, but they can be at different levels. They have to have the same ancestor, but so it's not true cohyponyms.
Okay. So thank you once again, Hinrich, for coming here and giving your presentation.
Thank you very much.